of yesterday's class, we introduced a new type of heat equation. So basically, it's what I wrote here in the yellow box. Okay. So the PDE itself is still the same, and we have the same initial condition. So what's different is actually on the boundary condition. So if we look at it here, so we say the unknown function at 0 is tau 1, and the value of the function at L is tau 2. So this means instead of fixed values of the function at the two ends to be 0, we actually enforce two different values for the function at the two ends. All right, so this is the troublemaker, and we need to figure a way to solve this heat equation. So last time I actually derived a formula for you, and basically we needed to do the change of variable. So we cannot solve the original unknown u xt directly. Instead, we solve another function wx of t and phi of x. So it is the two functions wxt and the phi of x that share the difficulties of the original. So we can solve them together. All right, so today I'm going to give you a specific example. So look at this example I have shown you here. So this is the PDE. So there's nothing special for the PDE itself. So from here we say it's a heat equation. So the left hand side is u sub t, all right, and the right hand side is u sub xx, and this makes a heat equation. And we say, okay, we don't have to pay attention too much on the initial condition. So the initial condition, we don't worry about it, and we need to carefully check the boundary condition. So look at the boundary condition. We see that for this unknown function u, so when x equals 0, we say the function u equals 1. It's non-zero, it's 1. And what about at the other end? So on the other end, so, or let's say when x equals 5, 5 is another endpoint. So at 5, the function u equals 4. So it's another non-zero value. So one end is 1, and the other end is 4. So it's a heat equation with two different values at the two ends problem. Okay, so first we have to identify the problem, and then we use the corresponding formula to do it. All right, now let's figure out all the parameters. So in this case, k equals 7, right? Which is the coefficient 7, and the L equals 5. So how do we read the total length of the interval? So we can look at it here, right? So the x goes from 0 to 5. 0 and 5 are the two endpoints. All right, so L equals 5. So what is the tau 1? Tau 1 equals 1. So it's the left end, the value at the left end, and the value at the right end, tau 2 equals 5. I'm sorry, it's not 5, it's 4. It's 4. Okay, so these are the parameters of this heat equation, and then let's see how to solve it. But first, we know that we're going to use change of variable. So we're not going to solve for the function u directly. So we let u of xt be the sum of two functions. One is w of xt and plus phi of x. So please pay attention that the unknown w is a double variable function, and the unknown phi is actually a single variable function. Okay, so this is our strategy. Now let's solve the w and the phi one by one. So from last time, we know phi of x is a linear function, right? So from the lecture notes from yesterday, we know that the phi of x is a linear function with phi of 0 equals 1 and the phi of 5 equals 4. So the function phi of x is the function phi of x that takes care of the boundary conditions. Okay, so at 0 equals 1 and at 5 equals 4. So by this information, So it's a linear function and it takes two specific values at the two ends, and we're able to solve for this linear function. So now we can write out the formula for phi of x. So phi of x then equals what? Tau 2 minus tau 1 divided by L x 1. So this is the linear function that satisfies the boundary conditions. So we just need to plug in the specific parameters. So tau 2 equals 4, tau 1 equals 1 minus 1 divided by L, then L 5x plus tau 1 again equals 1. So we just do some simple computation. So 3 over 5 plus 1. Okay, or phi of x, we just need the answer. 3 over 5 of x plus 1. Okay, so this is the linear function we're looking for. So you can check, right? When x equals 0, so equals 1. When x equals 5, 3/5 times 5 equals 5 plus 1. I'm sorry, equals 3, and then plus 1 equals 4. Okay, so this is the phi. We have already calculated the phi. Okay, so now we're going to go ahead to calculate w. So how are we going to find out the w? So we know that w satisfies a heat equation. So w of xt satisfies a heat equation. So what is the heat equation the U satisfies? So we know that Wt equals 7W of x and x. So the W satisfies the same PDE that U satisfies because of the phi. We choose the phi as a linear function, right? And then the W is boundary value free. So at the two boundaries, the W equals 0. Again, due to the nice pick of phi of x. Okay, because of phi of x. And then what is the initial condition? What is the initial condition? The initial condition, we need to think about it. Okay, so let me write it on the other side. Okay, so what is the initial condition? So recall u of x 0. I'm sorry. Recall this change of variable equals w of x t plus phi of x, right? And then we replace the t by 0. So or u of x 0 equals w of x 0 plus phi of x. So we can simply derive that the initial condition for w is nothing but u of x 0 minus phi of x, right? So this is the initial condition. All right. So then is and we know that u of 0 of x, what is this initial condition? Is here, right? It's 3 minus x. So this guy is 3 minus x. All right. So then we know the initial condition for w. So it's 3 minus x minus phi of x. 3 over 5 of x plus 1. Okay. And then what is the answer? So let's do a simple computation. Okay. So we got a 2 minus 8 over 3x. So this is the initial condition for w. All right, so let's look at the heat equation star. So we know how to solve the heat equation star, right? So this is nothing but the first or the very simple heat equation we have solved at the first place. So then we know the solution of w of xt equals sigma n goes from 1 to infinity bn sine n pi x over L e to the power of negative k n squared pi squared t over L squared. Okay, so let's plug in the parameters. So sigma n goes from 1 to infinity bn sine, so L equals 5 n pi x over 5, and the k equals 7. So negative 7 n squared pi squared t over L squared, which is 25. Okay, so that's the w. This is the w, function w. And we also need to know what is the parameter or what is the coefficient Bn, right? So again, we have the formula. So Bn equals 2 over L, 0 to L, nothing but the initial condition of it, and multiply sine n pi c over L. Again, you don't have to use c. You just use any variable you feel comfortable with. All right, so we have 2 over 5, 0 to 3. I'm sorry, 0 to 5. And what is the initial condition is here? The initial condition is here, right? So it's 2 minus 8 over 3 c and sine n pi c over L d, and that's it. All right, so we figure out the last piece of the puzzle. All right, so let's connect the dots together to show the complete picture of the solution. All right, so what you want to show me is this first bubble. So let me know that your solution of u of xt is made of two parts, the w of xt and the phi of x. And then let me know what is the phi of x. So this is the phi of x you have computed, right? And then you have to show me what is the w. W is here, this bubble. This is the function of w. And then show me the last part, what the coefficient Bn. So this is the coefficient Bn. All right. So this is how we solve a heat equation with two different values at the boundaries, at the two boundaries. Okay. All right. So then let me give you a little bit of explanation, or a little bit of explanation about what happened at the end. So when time goes long enough for this type of problem, okay, let me draw a picture. Okay, let me draw a picture for you guys. So this is the coordinates from 0 to L. So this is the one-dimensional wave. Okay, you have, and I give you an initial condition. But here is tau 1, and here is the tau 2, and I give you an initial condition. So it's some function like this. So this is the u of x0 equals f of x. All right. And then I need to fix at the two boundaries, tau 1 and tau 2. Okay. So when time goes long enough, you guys can think about it. So what is the shape of u of xt when t goes to infinity? We always ask this question. So this is one way for us to check whether our solution makes sense. All right. So what is the shape of the of xt? So at the beginning, it looks like the blue curve is f of x. And then what happens when t goes to infinity? Again, so let's look at the solution here. See, because of the exponential decay, so when t goes to infinity, so let's look at it here. When t goes to infinity, so we have negative infinity here. So this exponential goes to 0. And because of the exponential goes to 0, so the whole, regardless of the value of Bn, the whole W goes to 0. Right? As t goes to infinity. Okay, however, our solution is not just the W. Our solution actually is W plus 5. Right? So then from here, when t goes to infinity, so the w goes to 0, but the overall solution becomes phi of x. So now we come up with a conclusion. So u of xt actually goes to phi of x. This is the eventual status. So what is the picture of phi of x? Now you guys may remember. So what is phi of x? Phi of x is the linear function connecting the two ends. So it's something like this. Okay, so this is the phi of x. So no matter how you draw the picture, okay, so no matter what is the initial condition could be the solid curve, could be like the dashed curve. something like this, but eventually they will all be the red curve, the phi at the end. Okay, so think about this case. So you have a warmed up wire of length L, and no matter how warm you heat it up, so you put one end at 0 and put another end at 100 degree. So and then that time goes, and when time goes long enough, what would be the temperature distribution on this wire? So it will be a linear distribution. So from 0 gradually increase to 100 to the 2 at the right end, and in a linear sense. Okay, so this is the distribution. Okay, so this is the story. All right, so let's summarize a little bit. Okay, so far, what kind of problem we have solved? So now, so far, we have solved heat equation. U sub T equals Ku sub Xx, right? This is the heat equation. So that's, again, so later on, you guys will see better. So U sub T equals Ku sub Xx. This is the signature of heat equation. So first, with U of 0T equals U of LT equals 0 condition. And the second one, okay, let me leave space. The second one is U of X sub X, 0T equals U sub X, LT equals 0. The derivative is equals 0, all right? And the third one is U of X, U0 of T equals tau 1, and the U of LT equals tau 2. So here I skipped the initial condition. Again, the initial condition does not make a significant difference, so I skipped them here. So we studied the solved heat equation. This is the heat equation with these 3 different situations. Again, let's draw the picture, okay? So this is 0 to L. So the heat equation means, let's still draw the initial condition by blue curve. So that means at the left end is 0, at the right end is 0, and in the middle, I don't know, it's arbitrary. So in the middle is U of X 0 equals F of X. So the blue curve represents the initial condition. And what would be the eventual situation? So as the temperature goes. So what would be the eventual solution of the U, of the function U, if I draw the picture? Because of the 2 ends are connected to 0, or always fixed at 0, and after time long enough, so the red curve, so actually the solution becomes 0. Okay, so this is the U of X T as T goes to infinity. Okay, goes to infinity. So it goes to 0 everywhere because the 2 ends are zeros. We always exchange temperature with 0. Okay, so eventually what we got will be 0. All right, so what would be the second situation? So let's give you the difference between the physical pictures. Okay, here again, so at the beginning is 0, at the end is L, and the initial condition doesn't matter. Okay, doesn't matter what is the initial condition. So initial condition could be something like, let's say, this. All right, like this. And however, in this time, we always require the derivative is equal to 0. The derivative equals 0. So U sub X L T equals 0, and Ux 0 L T equals 0. So we don't fix the value at the 2 ends to be 0. We just set their derivatives to be 0, and that means cannot go the temperature. We don't lose temperature, and we don't gain temperature. All right. So what do we have? So the eventual solution will be a constant, if you guys recall, right? So what is the value of the solution? Will be a constant. So u of xt will go to the constant is a constant. So what is the constant? The constant is the integral of 1 over the integral of the original. Basically, it's the average of the initial condition. Okay, the initial conditions is f of x, and we just integrate it throughout the domain and take divided by L, which is the average of it. Okay, so this is the second type of boundary conditions. And the last one, what we have here is, so here's the 0, here's the L. Actually, I have shown you just a moment ago. So let's say at the beginning, so we always fix tau 1 here, and we fix the tau 2 here, and this is the initial condition. Doesn't matter how it looks, initial condition. U of x 0 equals f of x. So what would be the eventual solution? What would be the solution when t goes to infinity? So it's nothing but a linear function connecting these two dots. Okay, so this is the u of xt will go to phi of x as t goes to infinity. All right, so look at the three pictures. In the three situations, the PDE is the same, right? The PDE is the same. The heat equation is the same, and the initial condition would be the same, could be the same. And what's different is the ending point. It's the situation when t goes to infinity, right? The first case, the solution goes to 0. The second case, the solution goes to a constant, and it's not arbitrary constant. It's the average of the initial condition. And in the last one is the linear function and connecting these two ends. All right, so different boundary conditions gives us different physical pictures. So that's the message I want to deliver. So we have to carefully look at the boundary conditions. All right. Okay, so this is one thing. And another thing is, now we are going to do some change. We're going to have some fun about the heat equation itself. All right. So let's say the topic is